Now that we kind of have our theoretical footing for electric fields and electric potential, we're going to move on to more application type situations, starting off by looking at capacitors, which are quite a ubiquitous electrical component. They're used in basically all electronics all over the place. If you ever open up any electronics, look at your motherboard or something, there will be capacitors. They come in different shapes and sizes. These two over here are kind of the two common ones you'll see. These flat ones like this, and then these other kind of can-shaped ones. This is blown up of that. Guess my white doesn't draw on that white very well. Anyway, these are called electrolytic capacitors, and these are very widely used. They're one of the things that can actually go bad on electrical components. So to get a capacitor, essentially what we do is just have two parallel plates, and we charge one plate as positive and the other plate as negative. And when we do that, we store charge on the two plates, and in a way it's kind of like a battery, but these can be charged and discharged way more times than a battery. I mean, these can be charged and discharged millions of times without degrading, but they don't tend to give off their energy slowly like a battery does. It's just a real quick discharge, so these have other types of applications. You'll use them in for like camera flashes and things like that. You can do all kinds of different things with them in circuits. And typically, in order to get a real high capacitance, you need these plates to be large, and you're not just going to make this huge plate. So what you do is you roll it up nice and tightly like this, and you just put some insulating material in between so that the plates aren't connected to each other. And this is how most of those electrolytic capacitors are made today. All right, let's look at some of the equations around capacitors. We have this new value here, this new quantity called capacitance. And basically, if you have a capacitor, as you increase the voltage applied to that capacitor, so you hook up a battery to it, you're going to build up a certain amount of charge. So as voltage goes up, charge goes up. All right, and so we can say that the amount of charge you store on your capacitor is proportional to the voltage you apply to the capacitor. And then we just have this constant of proportionality that we're going to call the capacitance. So it is the ability of the capacitor to store charge. If you have a higher capacitance, you're going to get more charge built up per unit voltage. So you can rewrite this C equals Q over V. Now keep in mind that Q and V, changing Q and V doesn't change the capacitance. The capacitance is determined by the physical makeup of the capacitor. So whenever you change, for a given capacitor, C is constant. So whenever you change Q, you're going to change V. So you cannot affect the capacitance of a capacitor by changing these two quantities here. Now we can do it by changing other quantities, which we will look at right here. So if we have this parallel plate capacitor, we're going to have an electric field going from the positive side to the negative side. Oh, by the way, the charge on both sides here is going to be equal, because we assume that it starts out neutral, and when current starts flowing from the battery, you get an equal amount of positive charge on one side and negative on the other. Essentially, the amount that left one side went to the other side. And when we're talking about the charge on a capacitor, we're talking about just the charge on one side, because the net charge is always going to be zero. And we never really have a negative charge value. Just by convention, we make our charge amount on a capacitor to be positive. Okay, so here's our electric field, and we know that the electric field from one plate is sigma over 2 epsilon naught, but since we have two plates and they're both charged, the positive plate is going to have a field in this direction, and the negative plate is also going to have a field in that direction, so they will add together, and so this just becomes sigma over epsilon naught. And sigma is the charge per unit area, so I'm going to write that as Q over A times epsilon naught. And since this field is constant, if we apply that to V equals ED, where we're going against the field, so we would have a delta V is going to be positive, so we're going to make our ED positive. And then we plug this in for our electric field, we can get the expression that V equals QA epsilon naught times D. And then if I plug this into my capacitance equation, we had C equals Q over V. If I plug that V guy in here, I'm going to get Q all over QD divided by A epsilon naught. The Q's go away, and we end up with epsilon naught A over D. Okay, now this is the equation. If we want to know the capacitance of a capacitor, these are the physical characteristics that actually change the capacitance. Epsilon naught, obviously not, but the area of the capacitor does. So if you have larger plates on your capacitor, then you can have a greater capacitance. You can store more charge per unit voltage, unit volt. And the separation distance, D, if you decrease the separation distance, then you get more capacitance. But this is a little tricky because you can't get too close or you're going to get some arcing across that gap. So there's kind of some engineering trade-offs that you have to be aware of there. Let me show you real quick. Grab my nice little applet here. So here's my parallel plates. As I apply more and more voltage, then I store more and more charge, as indicated by the little positive and negatives on there. Okay, but if I want to increase the capacitance, I have to change. Actually, let's throw capacitance on here. If I want to increase capacitance, I need bigger plates. Okay, oh, looks like we went off the scale there. So as the plate gets larger, the capacitance gets larger and smaller. As the separation distance gets smaller, the capacitance gets bigger. Okay, if I change my voltage here, I change the amount of charge that's on there, but you notice I'm not changing the ratio of charge to voltage, so the capacitance remains constant. All right, I'm back to the battle. All right, let's look. That's what we just looked at. Moving right along. There it's written nicely, in case you didn't like my handwriting. Let's look at how we can apply this to a cylindrical capacitor. Now, most all of the situations we're going to deal with are parallel plate capacitors, but occasionally they like to throw these weird situations at you, so we'll look at them, and basically we'll give you the formulas that you'll use on occasion. So for a cylinder, what this is the cross section. So you've got a solid wire on the inside and then a hollow cylinder on the outside, and this can be a capacitor if you charge one of those elements as positive and the other as negative. You can store capacitance that way. So here we're going to start out looking at the electric field due to a wire, which we derived way back in the day, 2 pi epsilon naught over r, so it decreases as 1 over r. And if I rewrite that lambda as q over L, because that's charge per unit length, and then I've still got 2 pi epsilon naught r over here. In this case, we don't have a constant electric field, so we're going to have to integrate to get an expression for our potential, and then we can plug this potential into our C equals Q over V equation once we get it. And so we're going to integrate from, just in general, from A to B, negative E dot dl. Okay, so in this case, that's going to work out to be negative Q over L times 2 pi epsilon naught, and then we're going to have my dl, we're going to move just radially, so it becomes a dr. So I get dr over r from RA to RB. So I'm coming in from the outer edge. Now, if you remember, the integral of 1 over r gives you the natural log. So we've got negative q over L 2 pi epsilon naught natural log. It's going to be the natural log of RB minus the natural log of RA. And if you remember your natural log rules, that means you can write it as RB over RA. And now, just to get rid of that negative, we're going to flip this, which is another one of those natural log rules. Hope you remember all of these wonderful natural log rules. Okay, 2 pi epsilon naught natural log of RA over RB. Now, we'll plug that into this guy, but I'll do it down here. So we're going to get Q over this whole thing, Q over L 2 pi epsilon naught natural log. Oh wait, that's not down there. Erase. This is a very beautiful compound fraction thingy we got going on here, huh? Alright, Q's go away, and then we put stuff up top like we should, and we end up with 2 pi epsilon naught times the length of our capacitor. So that's the the length of the cylinder divided by the natural log of RA over RB. And there's a nice little formula you should write down to use for cylindrical capacitors. Alright, one more. We're going to do a spherical capacitor. This kind of looks like the picture for a cylindrical capacitor, but I want you to imagine these are cross sections of 2 concentric spheres. We've got an inner sphere of radius RB, an outer sphere of inner radius RA. I'll go a bit quicker on this one. So we've got the electric field is Q over, I go too quick, it gets ugly, 4 pi epsilon naught r squared. So you're going to plug this in to v equals integral v dr. Do the same thing. Anyway, I'll just cut to the chase and give you the formula. Ends up being 4 pi epsilon naught RB times RA over RA minus RB, all like so. Alright, so there's your formula for the capacitance of a cylindrical capacitor. See you next time.